All right, let's dive into one of the most powerful and, I gotta say, beautiful tools in all of calculus, the Taylor series. We're gonna crack the code that lets us see the secret identity of even the most complicated functions. So, yeah, let's get started. So get this. This is the big idea, the main theme for everything we're about to talk about. What if I told you that even these, well, messy functions, like sine or e to the x or the natural log, what if they could all be rewritten as simple, predictable polynomials? That's really the magic of Taylor series. It's all about taking something complex and approximating it with something simple.
Okay, so here's our game plan. First, we'll talk about this idea of a polynomial disguise. Then, we'll unveil the master formula itself. After that, we'll hit 4 essential series you should probably just memorize, see them in action with some examples, and then we'll wrap it all up by talking about why this stuff actually matters. All right, first up, the polynomial disguise. The basic idea is, well, it's kind of wild. If you know everything about a function, its value, its slope, its curvature, all that stuff, at just a single point, you can use that info to build a polynomial that's a fantastic approximation of the function, at least right around that point.
Think of it like this, right? Picture that smooth, wavy curve of a sine wave. Our goal is to kind of wrap a polynomial around it. A straight line, a simple one, might match the slope at one spot. A parabola? Well, that can match the slope and the curvature. And as we keep adding more and more terms to our polynomial, it just wraps tighter and tighter, becoming an almost perfect twin.
So, how do we actually do that? How do we build this perfect polynomial? Well, that brings us to the master formula. This is the key that unlocks the whole thing. And that key officially is called the Taylor series. You can think of it as a recipe for turning a function into an infinite sum of terms. And here's the crucial part. Every single term in that sum is built using the function's derivatives, its slope, its curvature, and so on, all figured out at one single, specific point.
Now you're going to hear 2 names thrown around, Taylor and Maclaurin. And the difference is actually really simple, but it's important. A Taylor series can be centered at any point we want. We just call it A. A Maclaurin series, that's just a special name for a Taylor series that's centered specifically at x equals 0. It's honestly the one you'll see most often, but it's just a special case.
Okay, here's the formula written out the long way, and you can really see how it works. The first term, f of a, just matches the function's value at our center point. Easy. Then this next term, the one with the first derivative, that matches the slope. And the third term, with the second derivative, matches the curvature. See the pattern? Each new term just pins our polynomial down more and more accurately.
And here's that exact same formula, but written in its super compact and powerful sigma notation. This is the whole recipe in one line. It just tells us to add up terms from n equals 0 all the way to infinity, where each term follows this exact pattern, the nth derivative at a divided by n factorial times x minus a to the n.
Okay, so you could derive every single series from scratch using that formula. But let's be real, in practice, mathematicians and scientists use shortcuts. So this next section is all about the 4 essential pre-built Maclaurin series. These are the ones that form the foundation for pretty much everything else. And here they are. Check out the beautiful patterns, right? The series for e to the x has all the powers of x. Sine only uses the odd powers and flips its sign back and forth. Cosine uses just the even powers and does the same thing with the sine. And the geometric series is the simplest of all, just 1 plus x squared and so on. But, and this is super important, look at the converges for column. The first 3 work for any x you can imagine. But that geometric series, it only matches the function when the absolute value of x is less than 1. That's a huge detail to remember.
Theory's great and all, but you don't really get it until you see it in action. So let's work through a couple of examples and see how we can actually use these tools to solve some problems.
All right, for our first example, let's find the series for e to the negative x. Now, instead of busting out all the derivatives from scratch, we can be a little clever here. We already know the series for e to the u, right? So we can just swap out the u with a negative x everywhere we see it. And after we simplify, boom, there's our new series. It's basically the same as the one for e to the x, but now the signs alternate. Plus, minus, plus, minus.
Okay, that was a nice shortcut. But what happens when we can't use a known series? What if we need to find a Taylor series that isn't centered at 0? Well, now we gotta roll up our sleeves and use that master formula directly.
Let's find the series for the natural log of x, but this time centered at a equals 2.
So step 1 is just methodical work. Calculate the first few derivatives, f of x, f prime, f double prime, and then plug in x equals 2 for each one. Now step 2, this is the creative part. We look at our results and try to spot the general pattern for the nth derivative. Once we've got that pattern figured out, we plug it straight into our big formula. And finally, we simplify. And watch this. This is the cool part. You get this beautiful cancellation with the factorials. N minus 1 factorial over n factorial just simplifies down to 1 over n. So satisfying.
And there it is, our final result. After all that work, we have this clean, elegant polynomial representation for the natural log of x, and it's a perfect match for the function as long as we stay close to x equals 2. So, we've done a bunch of math, but what's the big picture here? Why does any of this actually matter once you're out of a calculus class? Let's zoom out for a second and look at the real power of these things.
Okay, the number one takeaway is this. Taylor series turn really complex functions into simple polynomials. And why do we care? Because polynomials are awesome. They're easy to work with, they only use basic arithmetic, adding and multiplying, which is something computers can do incredibly fast. I mean, this is literally how your calculator finds the sine of 2.3. It's not looking it up in some giant table, it's just calculating the first few terms of a Taylor polynomial to get a super accurate answer, like instantly.
And that kind of leaves us with a final thought to chew on. If basically any smooth function can be disguised as an infinitely long polynomial, what does that really tell us about the fundamental nature of math? Does it suggest that, on some deep level, a lot of complex things in the universe are just built from really simple, repeating rules of arithmetic? It's a pretty fascinating question about the very structure of how things work.